Hey everyone, it's Cal here from Wise Guys Tutoring. I'm back to solve some more EmSAT Math practice questions. As usual, I'll be going through the topic as well as solving the problem, so you have, a holistic understanding of each topic. Let's get started. First one is statistics. So it says, summary statistics for the number of campsites in different Emirates in the UAE are as follows. So we have a bunch of information. We'll get to that soon. A check of the data shows that 5 had been subtracted from every value to bring the minimum to 0 for some calculation purposes. If 5 is added back to every value, what will now be the interquartile range and the standard deviation? So let's look at some of the data they've given me. They've given me the minimum and the maximum. So that's literally the minimum number of campsites in some of the Emirates or one of the Emirates. And this is the maximum number of campsites in one of the Emirates. Okay. Let's talk about Q1, median, Q3. Now what these are based on position. So let's say I have this kind of data. I'm just making up any kind of data set right now. The median here, the median represents the value which is in the middle location. Okay, so median is the value in the middle location. And remember, it doesn't matter what the value is. Whoever is in the middle when they are ordered from smallest to biggest is the median. In this case, hopefully you've guessed that this is the median, right? There's 3 below him, 3 above him. He's in the middle position. This is the median. In our case, that's what 61 means. Now Q1 and Q3, those are the quartiles. This is called the lower quartile or first quartile. This is the upper quartile, Q3. What they are is the middle of that half and the middle of the upper half. Okay, they are quartiles because they represent a quarter of the way. Basically, a quarter of the data is below Q1 and a quarter of the data is above Q3. Okay, that's Q1 and that's Q3. When we talk about the interquartile range, what they're asking for is Q3 minus Q1. It's the range between them. It's the difference between them, right? In our case, right here in my little example, it's 3 minus 2. It would be 1, okay? But for us, in this real example, what is the interquartile range? So let's write it over here. Let's say interquartile range of the subtracted, right? They told us that this data is the one that was subtracted 5 from every data, right? So this one was Q3 minus Q1. We have Q3, we have Q1. So it was 95 minus 35. So the interquartile range of this, data that they manipulated is 60. Okay. There is another value which you can calculate, which is called range, just the range. And just the range is always the maximum value minus the minimum value. And in this example, it would have been 300 minus 0. It would have been equal to 300. But they're not talking about that, so neither will we. Goodbye, range. Now, the second statistic that they're talking about is the standard deviation. So when it comes to standard deviation, this is also a measure of dispersion. These are measures of dispersion. They're basically measuring how far my data is from the center, which is, for example, the mean or the median. The mean and median and mode, as you've seen in my previous video, I'll put the link up there, they are measures of central tendency. They're aiming at the middle. Whereas IQR, the interquartile range, and the regular range, and the standard deviation, they're all trying to tell you how dispersed is your data. They're trying to tell you how far from the center is my data. And I'll give you a little drawing here as an example. There are 2 sets of data that can have the same mean. You can have something like this, where the mean is here. Or you can have data like this, right? Where the mean is also here for the orange one. So they have the same middle, but look how narrow this one is. The orange one, all the data points are very close to the center. So this one will have very low standard deviation. It will have a very low interquartile range. Whereas that blue one, you can tell it's much more spread out, the data, the values are very far from the center. They will have a very high standard deviation or a very high range. Well, higher than the orange one anyway. Technically, if you care to know, you're given this equation the way that you calculate the standard deviation is you measure the difference of each data point, the difference from the mean, you square it and you divide by how many entries you have. You don't have to know that at all for this question. So let's just move on. The standard deviation here is 58. So I'll put that sigma of that minus 5 data is 58, right? So now they tell me if I was to add 5 back. So if I was to add this 5 back, what would happen to the IQR and what would happen to sigma? So if I were to add 5 back, here's what would happen. These are measures of dispersion, right? So it's like this is my original data, right? I've subtracted 5 and now I have this. So if I add 5 back to every single value, what's going to happen is a shift. This whole thing, every single point on this curve is going to shift by 5. So this mean will become whatever it was plus 5. Okay? The IQR, the Q1, the Q3, everybody will stay in the same position. They'll just be increased by 5. All of them will be increased by 5. So if you're adding a constant, it will not change the IQR. Even if you're subtracting a constant, it will not change the IQR. I'll give you a quick example up here, right? Remember my data. Let's say I add 5 to everybody. Let's see if it changes anything. This would become 6, 7, 7, 8, 8, 8, and 9, right? Who's in the middle position? It's 8. He's 5 more. Who's in the Q3 position is 8. Who's in the Q1 position is 7. So whereas my previous difference between Q3 and Q1 previously was 1, now when I added 5 to everybody, it's still 1. It's still 8 minus 7. It doesn't change the IQR and it does not change the standard deviation. If you are looking at these two curves, they are just as spread out as before. Nothing's changed in terms of the spread. I've literally just shifted everything 5 down the line. So that's why the answer is going to be 60 and 58, because adding or subtracting a constant from a set of data will not change the IQR and will not change the standard deviation either. Okay, let's go to the next one. So this one's got a couple of combined triangles there. It says, what is the measure of angle TRU in the triangle? So in case you're not sure, when you're reading angles and it says TRU, that means you're at T, you go to R, you go to U. It's the angle is at the middle letter, right? It's this angle right here, TRU. They tell me that RS is equal to RT is equal to TU. And the measure of this angle here is 50, right? Remember, RTS, angle of T. So what do I do with this? So if they want this angle up here, and I know that this is an isosceles triangle, I also know that since these two sides are congruent, then the base angles are also congruent. So this angle is equal to this angle, right? I can also figure out this angle because along with 50, they form a linear pair because they add up to 180, right? Whenever you have one line which is being split like that, that's 180 degrees. So this one must be 130, which is 180 minus 50. There you go. Now, angle sum theorem tells me that in any triangle, all triangles, the total, the sum of all the three angles is always 180. Okay? So that means I have 180 degrees minus 130 degrees. How much is left for these two little guys? Well, there's 50 degrees left to split between him and him. As I said, it's an isosceles triangle. That means both of these base angles must be equal. That means their measure is going to be 50 divided by 2. Each one has got to be 25 degrees. If it's 25 and 25, just to do a quick check for myself, right? You check yourself before you wreck yourself. 25 plus 25 plus 130. Yeah, that's 180 degrees. I'm good. So the answer here is going to be 25 degrees. Good. Let's move on. This one is a little bit tricky. It says, when the area in square units of an expanding circle is increasing twice as fast as its radius in linear units, what is the radius? So first of all, when they're saying area in square units, they're just, it's just the area. area is always given in square units. They could have put in centimeters squared, where this one is in linear units. That means like centimeters. It's not centimeters squared. That's all they're saying. Basically, they have the same units. So when the area of an expanding circle is increasing twice as fast, when you have these questions about increasing twice as fast, and they're talking about a rate, okay, a rate of increase or decrease relative to another variable, what they want you to do is find the derivative, because the derivative is the rate. The derivative is a rate of change. It's a slope. It's a gradient. That's what derivatives are. So basically what we are going to say is that the area of a circle, hopefully you know that it's pi r squared, right? So it does depend on the radius. Now if they say the rate of change of the area, it's changing twice as fast as its radius, what they're trying to say is that the derivative of this area with respect to the radius has to be equal to 2. Okay, twice as fast. The rate of change of the area is 2. Now, what is the derivative? What is dA over dr? When we say dA dr, let's take it to the side. That means what's the derivative of this expression when I'm looking at r? So that means what is the derivative of this expression? Now this expression, r is the variable, pi is just a constant, right? So pi can wait outside. How do I find the derivative of r squared? Well, that's just the power rule. And we've talked about the power rule. I'll put the link up there. The power rule states that you decrease your power by 1 while bringing it down as a coefficient, a multiplier, right? So the 2 goes down, becomes 2r, and instead of a 2, you're left with 1. Now if I clean this up a little bit, it's 2 pi r, right? R to the 1 is just r. So the derivative is 2 pi r. Now I'll take these two guys and I will equate them, right? I know that the rate of change, the derivative of a with respect to r, the rate of change is twice as fast as the radius. That means dA over dr is 2. And I also know that the derivative, the rate of change, when I do the derivative using my nice power rule, I get 2 pi r. So that means I have 2 pi r. So what must r be, right? They're asking me to solve for r. If I got to solve for r, then let me divide here by 2 pi on both sides. These cancel out, and I'm left with the 2 cancels with the 2. You get 1 over pi equals r. And that is answer number D. So the takeaway from here is when they're talking about the rate of change of something with respect to something else, you got to think derivative. Okay, here they're talking about the area is increasing twice as fast as its radius, right? They're both changing, but there's a relationship there, a rate of change of one based on the other. So as one is changing, the other is changing twice as fast. That's why dA over dr is equal to 2. At the same time, we equated the derivative. We found the derivative using the technical way, right? The power rule, and we've equated them. And that's how we solve for r. I also just want to make a small point here. I know, I've put r on the right here. I know a lot of students really force themselves to, if they're looking for the variable r, they really want it to be on the left. We're always used to saying x equals 4. It doesn't matter, guys, okay? Right, left, it really doesn't matter. Make your life easier. If you see it's on the right, solve it on the right and then switch it later, whatever. It's all good. Okay, let's move on to the next one. This question says, for what value of k will x plus k over x have a relative maximum at x equals minus 2? So this is where derivatives are very useful when they're talking about maximums, okay? I'll give you a quick recap of derivatives. Let's say I have this kind of curve. So the derivative of this curve means it's the gradient of this curve, or the gradient of the tangent to the curve. That means if I'm asking you for the gradient of this curve, it's not like a straight line, right? If it's a straight line, let's say something like that, well, the slope is constant. Anywhere I look, the slope is exactly the same. If I'm looking at this curvy guy, the red curve here, well, look, the slope which is measured by the slope of the tangent to the curve. Here it goes, you know, kind of upward that way. But as I get closer, see what happens? It starts to flatten out, right? And actually at the top, right here at the maximum, the slope is 0. It's straight up flat. And then it starts to go down again, you see? It starts to go down, then it starts to go down more, and whatever. So at the maximums and minimums, it's very useful to know that the slope of this curve is 0, right? So at the maximum, the derivative, which is the slope, is equal to 0. And that's what we're going to use, okay? So why don't we do this? Let's call this function, let's pretend it's, you know, y equals x plus k over x. So what I'm trying to find here is when is the derivative of this equal to 0? So first we got to find the derivative. Let's call it y prime. What's y prime of this bad boy here? Now the rules when you're doing derivatives and integrals, we don't like to have anything in the denominator, right? It's much easier to put him up. So we can rewrite this as x plus k to the x times x to the minus 1. When you have x to the minus 1, that's the same thing, right? That's the same thing as 1 over x. And what I have here is, in fact, k times 1 over x. So all I'm going to do is, instead of putting it 1 over x, I'm going to rewrite it like this. And the reason I do that is that I can use my power rule that we saw earlier. I can bring down the exponent and decrease it by 1. Okay, so let's continue. The derivative of x is just 1. And the derivative of this guy, like I said, you bring the minus 1, k is a constant, right? You bring the minus 1 down as a multiplier of x, and it decreases by 1, it becomes minus 2. So that's what we have. Now let's clean it up a little bit. You have 1 plus negative k, so instead of plus I'll just put minus k, and that's times x to the minus 2. And as we saw, when you have an exponent which is negative, what it means is flip, right? Go downstairs. So this becomes 1 minus k over x squared. So the x to the minus 2 means flip it over. It goes down. Okay. Now I have this. This is the derivative. This is the equation, okay, for the slope at any point on my curve. Because if we were talking about a linear function like this purple one, and you would say, hey buddy, what's the slope of this curve? I would tell you, well, it's 3 or something, right? Because it's the same everywhere. It doesn't change. It doesn't matter. But if you told me on this one, you would say, hey, what's the slope? What's the gradient? I would say, well, buddy, you gotta tell me where, right? It's different. When x is here, it's something, and when x is like 3, it's totally different, and when x is 2, it's completely different. You have to tell me where. The gradient, the slope of this curve, of these lines that I've drawn, it changes depending on x. That's why you'll always get an expression in terms of x, right? If it's linear, we used to just get, oh, the gradient is 3 or the gradient is 2 or whatever, because it's constant throughout. But when you have a curve, it is not constant, okay? Anyway, so now we have the expression for the derivative. We have the expression for the slope at any point x. Now, I have been told that when x is negative 2, at x is negative 2, I have a relative maximum. I have some kind of maximum up there, right? So that means the gradient, the slope, the derivative will be 0. So at x equals minus 2, I'm going to set my y prime, I'm going to set it to 0, and I'll solve for k. So 0 equals 1 minus k over minus 2 squared, right? This is going to give me 0 equals 1 minus k to the 4. I'll go just over to the side. So k to the 4 equals 1, right? I'm just adding k over 4, adding k over 4. So I end up here, and then I multiply both sides by 4 to get rid of my denominator. and I know now that k is equal to 4. That's the final answer. K is equal to 4. I'd just like to clarify one thing when they say relative maximum. Some curves have multiple minimums and maximums, or maxima and minima as they call it. So it could be something like that, right? So this might be an absolute or a global maximum, whereas these ones are relative. That's all they mean. For our case, it doesn't matter because either way, they all have a gradient, a derivative of 0, right? Your gradient goes up, up, and then it starts to flatten out, and then it starts to go down again. And even at a minimum, see, it goes flat, and then it starts going up. I'm just following the curve. That's all I'm doing, right? So anytime you have one of these maximum minimum points, you're going to have a derivative of 0, and that's what we use. Okay, let's do the last question. Okay, so this is another question about rate of change and derivatives. So let's try to do it based on what we learned in a couple of questions ago. So it says the radius of a circle is decreasing at a constant rate of 0.1 centimeters per second. So again, you got that, decreasing at a rate. So in this case, we need to use the derivative, right? Before we continue the question, let me just get through with this one. So it says the radius of the circle is decreasing at a constant rate of 0.1 centimeters per second. That means it's the change of the radius per change in time, right? It's centimeters per second. And they tell me it's decreasing. So I know it's going to be a negative change. And it's a constant rate of 0.1. So here you go. Now I know that dr over dt is minus 0.1. The rate of change of the radius per second, centimeters per second, is decreasing by 0.1. All right. So in terms of the circumference, what is the rate of change of the area of the circle in square centimeters per second? So let's forget about the circumference part for a second. Okay. Let's talk about the change of the area of this circle. As we saw earlier, it's the same thing. Let me use like a light blue for the area. We can say that the change in the area with respect to the radius, we've seen that before, it's basically the derivative of the area with respect to radius. We know the area of a circle is pi r squared. So what is the derivative of a? You can write it as a prime, or you can write it as dA dr, they're the same. So pi is a constant, right? R squared becomes, so pi can wait outside, becomes 2r to the 1. So I'll clean it up a little bit, rearrange so it looks like 2 pi r. That's the derivative here. So dA dr is 2 pi r. Okay? Now what they want is the area of the circle, the change of the area of the circle per second. So actually what they're looking for dA dt, right? The change of area over change in time per second, right? Centimeters squared per second. So how do I do this? Well, I'm going to combine these two guys. I'm going to say dA over dr times dr over dt. And hopefully by now you've seen enough algebra to know that when I multiply by something and divide by it, well, those two just kind of cancel out. And I'm left with dA dt. So this is good. This is what we're going to do. We're going to be multiplying dA dr times dr over dt. So this ends up being 2 pi r, right? I'm just taking that light blue one, times minus 0.1, which is that one, the dark blue one. Now hopefully you'll notice that 2 pi r, maybe that looks familiar. It should, because that's actually the circumference of a circle. 2 pi r, right? Circumference of a circle, meaning the perimeter of the circle. So instead of 2 pi r, I'm just going to put c instead. So it's c times minus 0.1. And normally we like to put the number before the variable, as you probably well know. So it's minus 0.1 c. Which one is that? Looks like B. There you go. So the answer to this one is B. Hopefully you were able to follow along a little bit better in this one after having seen the previous question about rates of change. This is derivatives. You're dealing with pre-calculus, so you may not have seen it But hopefully now you can at least manage when you see rates of change, especially when they talk about, you know, area with respect to the radius, or the radius with respect to time. This is what they're talking about. Okay, so I hope that was helpful. Before you hop off, please make sure you subscribe. Also, if you have any comments, questions, suggestions, even if you have any problems or something you want me to solve, then just leave me a message here or add me on Instagram at WiseGuysUAE and DM me there. Also, you should know that I offer an EmSAT Math workshop. It's an online group class, so get in touch with me if you want to take part. Take care, guys. I'll see you in the next video very soon.